This application is my favorite because it's what I do. I measure and build equipment to measure the energy efficiency in air conditioning process. We have to realize with what we're doing with air conditioning is we're removing energy from the house. We expend a tremendous amount of energy to remove energy from the house. And what I'm saying we'll do is we'll take that energy, and when we reject it outside at a higher temperature, we'll use that and recover that energy to generate electricity. One way we check that our measurement is accurate is the energy rejected outside, out of the condenser outside, has to equal the amount of energy that is absorbed within the house and the amount of energy that is pulled in from the grid. These all have to balance out in the end. So the amount rejected outside is equal to the amount of energy we soak up inside the house plus the grid. The EER, the energy efficiency ratio, is one of the things we use to rate air conditioners. So basically it is how much cooling do we get in the house and how much electricity does it take to get that cooling. So that would be the BTUs in the house divided by the number of watts it took to get that. So basically when we add that up, let's just throw some numbers out for this and say, okay, we're going to put 1 ton of AC air conditioning, 12,000 BTUs, at an EER of 10, which is a pretty good unit. So we got 1,200 watts is what we're using, or 4,094 BTUs. Basically what we're seeing is that 1/4 of the energy that's being rejected outside has actually come from the grid, and the rest is from the energy soaked up from inside the house. From the patent video, you see that we should be able to get work out of it that is proportional to the density ratio of the refrigerant or fluid that we're using. And I'm going to go with 134A. It's one I'm most familiar with. And so we go to RefProp and we say, okay, the air is rejected outside at 120 degrees F. But if you look at the density ratio between the liquid density and the gas, it's 1/16. All we have to do is be better than a quarter to be able to get enough electricity out of the system outside to cover all the energy, all the electricity that we came in from the grid. So it's possible that we can recover all the energy we reject outside. If you're not really excited about this, you're not paying attention. My electric bill goes up huge amount in the summertime, and sometimes the grid gets knocked out because everybody's trying to cool their house. We pretend global warming is not an issue, but hey, it is. And you could tell that by the grid and how much electricity we use to have to cool our houses down. So what I'm saying is the possibility is that we can cool our house, recover that energy, and use it to generate electricity. I can think of 3 or 4 ways to do this that I think would work really, really well. This computer simulation right here is one that's a Cascade unit, would actually be a retrofit. But what's really cool about this is we don't have to do this. We have to put this technology on existing companies that have existing infrastructure to put systems out in the world. They already can do this. We don't have to go to manufacture it. We can just put our technology on everybody else's air conditioner.